اوكي يا جماعه هنبتدي. قبل بس ما نبتدي، واحد منكم سالني امبارح سؤال، الحقيقه كان سؤال كويس تمام، عشان اللي انا قلته كان confusing شويه بالنسبه لماكسويلز ايكويشنز تمام. اللي انا قلته ان ماكسويلز ايكويشنز ما هياش consistent unless ان انت to impose الكرنت conservation تمام. هو دوت ممكن يكون شكله غريب شويه بالنسبه للنولج بتاعت الالكترومagnetism بتاعتنا تمام، بس انا في الحقيقه ما كنتش بتكلم على الالكترومagnetism قوي قد ما كنت بتكلم على set of equations بتوصف اي physical system in general ممكن يبقى ليها الفورمولا تمام. ف قصدي ايه تحديدا؟ احنا مثلا لما بناخد كواسو equation ماشي، النقطة سكوير فاي بتساوي رو او كيرل بي بتساوي جي. الطريقة اللي بنفكر بيها عادة في الايكويشنز دي بتبقى اوبريشنال شوية. بمعنى ايه؟ بمعنى انت اديني رو وانا هطلع الفاي، والفاي هتوصف لي السيستم كله، وممكن استخدم الفاي في ان انا تو تراك الفورس والتراجكتوري بتاع بارتيكل تشارجد اندر ذس فاي تمام. فهي تعريف اوبريشنال شويه، بمعنى اديني رو اطلع لك الفاي، اديني جي اطلع لك البي تمام. فبالنسبه لدوت لما انا اجي بقى احط الاربعه ماكسويلز ايكويشنز مع بعض، هيبقى عندي هنا اثنين انبوتس رو والجي تمام. الاثنين انبوتس دول انا حاططهم بشكل يعني اوبريشنالي زي كده، اكني حاططهم بشكل اربيتري. طبعا عشان تاني الكونسيستنسي بتاع ماكسويلز ايكويشنز الاثنين دول لازم يبقوا ريليتد سام هاو عشان السيت كلها تبقى كونسيستنت، والريليشن دي اللي هي الكونتينيوتي ايكويشن تمام. تاني لما بتفكر بالطريقه دي، لكن انت ممكن تفكر بطريقه ان انا عندي collection of physical quantities اللي هي الالكتريك فيلد والمagnetic فيلد زائد الرو والجي تمام. دول physical quantities انا بقيسهم، ودي الايكويشنز الريليتنج them كلهم مع بعض تمام. والست دي طبعا كونسيستنت مفيش اي مشكله تمام. طيب هي ليه الطريقه الغريبه اللي انا بفكر فيها دي ليها معنى، او يعني هتفيدنا في ايه بعد كده؟ في الحقيقه بتفيدنا لما بنيجي نعمل شغل اكتر من كده شويه على السيت اوف كلاسيكال فيلد ايكويشنز. لما اجي بفكر في الكوانتايزيشن بتاع الفيلد، لما اجي بفكر في الكوانتايزيشن بتاع الفيلد اوقات كتير جدا لو انا طبعا بتعامل مع جيج فيلد زي كده بوصفه باي ميو تمام، ما بقاش فيه مشكله في ده، لانه اوتوماتيكلي هلاقي الجي زي ما احنا شفنا من الايكويشنز تمام، اوتوماتيكلي الجي كونزرف، فمفيش مشكله في الجيج فيلد اللي هو بالشكل ده. لكن خليني اعمل تويكينج او تشينجينج شويه في الجيج فيلد اللي عندي تمام. مش هخليه جيج فيلد اصلا، هخليه فيكتور فيلد. فيكتور فيلد بمعنى فيلد ليه 4 كومبوننتس، فاي والاي فيكتور تمام، وما هواش جيج فيلد، يعني ما هواش انفاريانت اندر الجيج ترانسفورميشن اللي بتحول لي الاي من اي ميو ل اي ميو زائد بارشل ميو الفا تمام. الكترومagnetism invariant under this transformation تمام. بس انا ممكن استخدم جيج فيلد اوصف بيه حاجات عندي في البارتيكل فيزيكس، وعندنا اكزامبل لده تمام. ما يكونش جيج فيلد اصلا، فيكتور فيلد يعني مش جيج فيلد اوكي. في الحاله دي لما اجي اعمل كوانتايزيشن او افكر في كوانتايزيشن لفيلد ما عندوش ده تمام، الفيلد ده عاده ممكن يبقى ماسيف او مش ماسيف جيج فيلد، سوري فيكتور فيلد تمام. نفترض ان هو ماسيف فيكتور فيلد. ماسيف فيكتور فيلد بيبقى ليه 3 فيزيكال كومبوننتس مش 2 بس زي البولاريزيشن دايركشنز بتاعت الفوتون. anyway لو انا مثلا بتعامل مع فيكتور فيلد زي كده وبفكر في الكوانتايزيشن بتاعه، الكوانتايزيشن ده مش كونسيستنت الا اذا كان الجيج فيلد ده كابلد مع كرنت تمام، الكرنت ده كونزرفد. لو الكرنت ده كونزرفد يبقى الكوانتايزيشن بتاع الاي جي فيلد ده كونسيستنت. ماشي؟ اوكي؟ فعشان كده بس يعني ايه بدي هنت ان انت تحاول تفكر in terms of this way of thinking versus ان انت عندك physical quantities تمام وبتقيسهم والphysical quantities دي طبعا consistent مع الفيلد equation او consistent مع بعض في equations. تمام؟ بس انا حبيت بس انوه على ده عشان ممكن يبقى الكلام بتاعي كان confusing شويه وانا بتكلم على الليفل دوت، بس انا كان قصدي في الحقيقه ان انت تفكر بره السات دي. تمام؟ يبقى عندك فيكتور فيلد وتفكر بره السات بتاعت الالكترومagnetic. ماشي؟ anyway نكمل بقى محاضرتنا النهارده عن الكيرفتشر تنسور. طبعا على المناقشه دي بس بقول لك ان الطريقه الاوبريشنال اللي انت بتفكر فيها دي ان انت جيفن رو جيفن جي تمام وبنشوف الكونسستنسي دي مفيده صح. دي مش يعني مش حاجه كده متعلقه في الهواء. جميل. So let's start talking about the curvature tensor. So last time what we ended up with was actually this caricature equation. We have some tensor which is equal to t mu nu more or less, and we know that this guy here on the left is some kind of derivative of the metric, okay, up to second derivative could be very similar to the idea as we said of Poisson equation. A plus square phi is equal to rho. So on the left hand side we have derivatives of the potential. Remember this is a function of the potential in general relativity which is the metric. And on the right hand side we have the sources. Okay? So how can we get this x mu nu? And we said that this x mu nu has to obey one single condition, which is the covariant derivative on x mu nu has to be 0. So the bottom line, x mu nu is a geometric quantity which depends on the metric through whatever connection, curvature, tensor, whatever, and it has this condition in order to get, of course, the conservation of the energy momentum tensor as a result of this. Okay? So we are going to construct this in terms of curvature. But let's first try to understand what we mean by curvature, because last time we had a discussion about connection and curvature and we did try to make a difference between them. But what is curvature? How I would know just in a hand-waving way if a surface has a curvature or not. Okay? So let me give you an example. First, a simple example which is flat geometry. So let's work in XY plane, okay? And let's have any shape like we have two curves, okay? Starting from one point and ending with another point. And let's take some vector, okay, starting from this point and try to parallel transport it to itself. If I do that, I just draw parallel vectors. I end up with the vector here, okay, using path 1, and using path 2, I should do the same. And I end up with the same vector. So if this is V1 and this is V2, I can see that V1 is equal to V2. Okay? So the change in V is 0. In this case, I know that this geometry, this surface, this two-dimensional surface is flat. Okay? But Does this make sense? Okay, let's try something more complicated, like a sphere. See if it's going to give us something different. Of course, we do the example of a sphere always for a curved surface because this is the simplest curved surface that we can describe. Okay? And let's try to do the same. Okay? Let's suppose that we have a curve here which is cutting the sphere into a half, and here also a half. And let's start from this point and end up at this point, and we have two curves. This one here, this let's say curve 1, and this one here, in this case, is curve 2. And let's actually define our vector in such a way it points always along the, I think this is called the latitude. Okay? خطوط الطول. Okay? ولا أنا قلقت؟ المهم, so it's going, of course, up, 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 up to here. It's going up, and then it has to go with the curve, right? Because this is going up, up, and it's going to end like that. And this one is again also going up, 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 and it's going to end like that. You can see that this is a track of vector 1, and this is a track of vector 2. Okay? So clearly, the change in the vector coming from the two paths, this is not 0. Okay? And this is telling me that there is a curvature here. Okay? So this is a simple way actually of tracking a curvature in a two-dimensional surface. Of course, no one knows how to do it for 3-dimensional or higher, but I think you got the idea. But the general idea actually is the following. Let's suppose that we have two vectors. A vector, I'm going to call it u, and another one which is w. Okay? And if I change u a bit, I'll have another vector here, and if I change w a bit, I'll have one here, so I'll have a parallelogram. And I'm going to check another vector, let me call it v, or old vector v, and see if it's going around here. Okay? And if it's going around and not actually coinciding with the first one, okay, then delta v is not 0. But I can actually write the curvature tensor in terms of the changes that happen to v itself. So change of v, rho, is some coefficient called r, rho, sigma, mu, nu, v, sigma, u, mu, and w, nu. So you can see the change in the vector is proportional to something times the vector v times the vector u and w. Okay? And this something here is what we call the curvature tensor. So this is why the change in vector in this way is related to the curvature tensor. And if the curvature tensor is 0 for whatever space, this change of v has to be always 0. Yes? What the difference between this and the circle?
The sphere, when you look the two vectors?
Right, this is not a flat geometry. This is very sketchy. Okay, I just meant that you repeat this here using u and w. That's it. Okay? but I didn't really want to follow the vector exactly, okay? But this is a curved space because the result is not zero, okay? This is very sketchy, but the meaning here is to keep in mind that I'm constructing this parallelogram using U and W, that's it, okay? And how the change of V is related to U and W and V itself and some coefficient which I'm going to define as my curvature. Okay? So this is the curvature tensor, R or Riemann tensor, okay, which is very important in studying, of course, any curved space-time. Of course, there are so many types of curvature, but this is like the simplest one. Okay? We define the curvature tensor in terms of the connection that we discussed last time in this way. So we have gamma, sigma, mu, lambda, comma, nu. This is a derivative. Comma here means partial derivative, okay? So when I say A, comma, nu, this is partial by partial x nu of A. Okay, so this is the definition of the Riemann tensor in terms of connection. And last time we defined our connection. And from this definition, you can see actually very important like symmetry properties for this tensor. If we write down, if we bring this indices down using G, we can actually do that like sigma, alpha, R, sigma, mu, mu, lambda. So this way we get, sorry, let me do it like sigma, alpha, sigma, alpha. So this is like, you can think of it as delta, okay? So we'll bring, confusing you, alpha, mu, nu, lambda. Okay, so all the indices are down. So for this tensor, for example, the first two indices are anti-symmetric, so I can change them. I can interchange them with minus sign. Okay, this is one property. And also the last two indices as well, okay? So these two indices also are anti-symmetric, okay? And the first and third are symmetric, okay? Let me do it this way. And the second and fourth are symmetric. Okay, so these are the symmetric properties of the Riemann tensor, which is not very important for you, but I just mention it here. What is important for us is what is called Bianchi identity. Which is saying that nabla lambda or mu nu alpha beta plus nabla beta or mu nu lambda alpha plus nabla alpha or mu nu beta lambda is 0. The importance of this identity is the following, that one can use it, okay, to construct a quantity which has this property. Covariant derivative acting on it is 0. Okay? But before we do that, let's define first a contraction of the Riemann tensor. So if we contract two of the indices of the Riemann tensor, let's suppose that we have R, which is lambda mu sigma nu, and now we are contracting, as you can see, the first and third indices. Okay, it's very careful. You should be careful here because, for example, if you contracted the first two, what you will get? Can you tell me? Because the first two are anti-symmetric, right? And the metric is symmetric. So contracting symmetric with anti-symmetric is 0. So if you contract the first two indices with the metric, this is 0. So this is why the first and third, since it is symmetric, this is going to give me a symmetric tensor, which is what we call Ricci tensor. This is Ricci tensor. And now one more contraction to Ricci tensor will give us R, or the Ricci scalar. Okay? So this quantity is called Ricci scalar. This is Ricci tensor. And I'm going to actually use Ricci tensor and Ricci scalar, okay, to construct this quantity. So you can work out this exercise. I'm not going to do it here. If you just contract this equation here with a metric, okay, like for example with u alpha or something like that, okay, you can end up with some equation which has covariant derivative acting on Ricci mu lambda minus half g mu nu times the Ricci scalar, okay, and this is equal to 0. This is an identity, okay, from the Bianchi identity, okay? You can derive it easily from Bianchi identity. Then Einstein knew that this is actually this is a candidate he was looking for, which satisfied this equation. And then he actually formulated his equation in this way. So basically what he did was said that R mu nu minus half G mu nu R is equal to 8 by Gn T mu nu. Okay? So this is Einstein field equation of G1. Okay? Of course, this is highly nonlinear equation, and it's not easy at all to solve it for even very simple systems. We are going to discuss now its solution for the spherical symmetric case, what we call Schwarzschild solution. Okay, but in general, solving this equation is non-trivial. Why? Because here you have derivatives of the metric up to second derivative, and this metric is 10 component in general, so it's not very easy to solve, and it requires that you have to impose some symmetry in order to simplify the equation a bit and to be able to solve. So usually we impose symmetry and then try to solve the equation. Very similar to what we do in electrostatics, for example. So if you want to solve this electrostatic equation, okay, for example, spherically symmetric charge distribution or axially symmetric charge distribution, of course this simplifies your equation a lot, because, for example, let's put it in terms of nabla dot E. Okay? So, for example, if you have spherical symmetry and you need to calculate the electric field, you would know that the E theta and E phi components are zero. So you care about just one component, and you try to solve this one component in this case. Very similar, in a very similar way we do here this, okay? By imposing symmetry, okay, for example, like the spherical symmetry, I can actually reduce the number of components of this metric to quite few. For the spherical symmetry case, I can actually reduce the number of components to only 2 components. So I have arbitrary function A of r plus B of r dr square plus r square d theta square plus sine square theta d phi square. Okay? So this is the general form for a spherically symmetric metric. Okay? You have 2 arbitrary function, and then you plug it in Einstein field equation here, and then you try to solve for A and B. Okay? So let's try to just write the results in case of a vacuum solution which is spherically symmetric. So this is like the field outside a spherically symmetric object. And you are asking the question what it looks like, what the metric looks like, and therefore what is the gravitational field looks like outside of this spherically symmetric object. Okay? And the result is that A of r, which is 1 over B of r, is going to be 1 minus 2 mg over r. Okay? This is a general solution you will get from this metric, imposing 2 conditions. First, that your metric is going to be Minkowski metric as r go to infinity in the very, very, very far away region. And second, that actually you're going to have like a point mass, okay? So your field, okay, will try to go to Poisson equation, or it will be obeyed by Poisson equation in the non-relativistic limit or in the classical limit, okay? So in this case, you will find that G00 is equal to 1 minus G00, which is A, okay, or minus A actually, is 1 minus 2 phi Newton, where phi Newton is just, maybe plus, actually. Maybe there is some sign here. So yeah, let's give it, yes, minus mg over r. Okay? So in other words, this spherically symmetric situation that you have is going to the Newtonian limit nicely. Okay? With these 2 conditions, you will get this solution to Einstein field equation. And let's actually see what are the properties of this solution? So first of all, as you can see by construction, that this solution in the limit of m goes to 0 or r goes to infinity, that this solution goes to Minkowski space, flat space, okay? And you can see from here, it's 1 minus 2 mg over r, and here this is 1 over 1 minus 2 mg over r. And you can see, by sending r to infinity, this is just 1. And sending r to infinity, this is just 1. And you are left with the Minkowski metric in spherical polar coordinates. Any question here? Any question? You have a question? Okay. So, yes. Read metric A? Okay. Good. So, first, in this case, in this specific case, we are actually looking for a static solution, vacuum solution, okay? And static solution means the following. A static solution has to have two conditions. One, the time variation, okay? Whatever coordinate you have and call it time, x, 0, t, whatever, all the component is time independent. So the partial derivative is 0, okay? This is condition 1. Condition 2 is that any mixed components like 0 phi or 0 x or whatever is 0. Okay? So this is the definition of a static solution. So for a static, spherically symmetric, vacuum solution, this is the only form you can have. A of R and B of R. Okay? By definition. For example, if you don't want static solution, but you want stationary solution which is like Kerr solution, rotating. So you are discussing a rotating black hole, not a static black hole. Okay? Not a black hole which is not rotating. Okay? In this case, you drop down this condition. And in this case, if you drop this condition, this is a stationary solution. Okay? And you allow for a mixed terms in the metric. Okay? Good. Any other questions so far? Yes. لما نحط الار بانفينيتي مش بانفينيتي لما نحط الار is very very large. Okay? So when you put r is very very large, this is not going to get affected. Okay? R is large, that's it. But here, when I put R is large, this term drops out, right? So this factor is becoming 1. And the same thing here also. This factor is becoming 1. But if you actually try to check this form of the metric, which is minus dt squared plus dr squared plus r squared, the rest, this is just Minkowski in spherical polar. Okay? And the most important properties here for this solution is that it has two weird points here. As you can see from the form of the metric, that there is something funny happen at r equals 0 and at r equals 2 mg. Okay? At r equals 2 mg, this component is going to be 0. This component is blowing up. Okay? And for r equals 0 is the same. Okay? This is going to be For r equals 0, this is going to go up, and this is going to be 0, the reverse. Okay? So this is very strange. And actually, these two funny situations, it took us decades to actually understand. So in the beginning, for example, Einstein was even confused about this horizon issue, okay? And he thought that this is a situation which is not physical at all. To have r, okay, like the radius is less than 2mg. In any case, so we have two strange situations. First, r equals 2mg. And r equals 0. The first one turned out not to be a singularity or a problem in the metric at all. In the beginning, most of the relativists thought that these 2 points are singularities of our description, which means that our description fails around these 2 points. Okay? So it's not a good approximation, or it's not good to work with closer to these values of r. Okay? But it turned out that this value of r is not problematic at all. Okay? This is what we call today coordinate singularity. Okay? Which means it is a fictitious singularity. It's a fictitious singularity because you are using a coordinate system which fails at some point. But if you change the coordinate system, you could actually describe this region that you have failed to describe here, okay, in a better way. Okay? So this is why we call it a coordinate singularity or fictitious singularity. Okay? The other one, it turned out to be actually not a fictitious singularity. It is indeed physical singularity, and it is signaturing or signaling the fact that your description is going to fail closer to this point. So this is what we call curvature. Or physical singularity. Okay? Okay? So in the rest, I'm going to actually have some discussion about certain coordinate transformation that we are going to use, maybe to make this statement much more clearer, okay? And also to study the structure of the black hole, okay? Like what is the general form, or how can I understand more the black hole physics, okay? So let me start with our metric here. And we are going to present a series of coordinate transformations which actually allow us to understand more the physics of this solution. Of course, this solution is very generic. So you can use this solution to describe a planet with huge mass, or a star, or a black hole, an astronomical black hole. Okay? So this solution has many, of course, usage or uses. Okay? But here we are trying to understand it in the phase of black hole more. That's to say, you have some astronomical object, and this astronomical object already burned its fuel, like a star, of course. already burned its fuel, and now it went into a collapse, a complete collapse, and becoming a black hole. Okay? So this is what we are about to study. So the radius of this star is already inside the Schwarzschild horizon. This R equals 2 mg that we have said. Okay? So starting from this metric, I'm trying to study a ray of light which is going radial, okay, with, for example, theta equals pi over 2 and phi equals some constant. You will see that dt, of course this is a null ray, I'm going to choose a null ray. A null ray means ds is 0. Okay? So if ds is 0, and if I have constant theta and constant phi, this is not there. And the only thing that I have is the dt square and the dr square, and they are related, of course. I can write this relation as dt by dr equal to plus or minus 1 minus 2 mg over r to the minus 1. Okay? This is the relation between the time and the radial coordinates. And you can see, if you put m to be 0, you will get actually dt by dr to be plus or minus 1, which is basically the light cone, the usual light cone that you have. Okay? This is R. The usual light cone that you have, okay, in flat geometry. Okay? But you can see that as we get closer and closer to R equals 2 mg, this light cone angle, which is used to be 45 degrees, going to actually get squeezed a little bit. So if I try to draw this, okay, if I have R and T here, and this is actually the Schwarzschild radius, 2 mg, what happened here is that very far away at R is large, I'll find that my light cone is as normal. When I get closer and closer, I'll get the light cone to be a bit squeezed. And the squeezing factor is coming from here. Okay? Because as R get closer to this value, okay, this value is going to be large, which means a large slope. A large slope means the light cone is squeezed. Okay? So somebody would say, okay, so in order to avoid this squeezing that we know now it is actually could be fictitious, I might change the coordinate and deal with a better coordinate. Like, I will actually take this dr here and integrate this to get some function of r, which I'm going to call r star. Now, t is directly related to r star, and the slope is plus or minus 1, and I can actually deal with this situation. So this is, choosing r star as a coordinate is going to keep the angle of the light cone open. Okay? So by doing that, I can actually, r star in this case is going to be a simple expression, which is r plus 2 mg then r over 2 mg minus 1, if you want to calculate it. Okay? And now by writing the ds square, you can see that it is 1 minus gm over r. minus dt square plus dr star square plus the radial part. Okay? You can see indeed the angle of the light cone now is kept constant. Okay? One can actually start to use another coordinate system. Let's use v equals t plus r star. Okay? And if we do that, we go actually to a coordinate system called Eddington-Finkelstein infalling coordinate system, which is basically given by the following metric. It is -1 minus 2 mg over r d mu square plus 2 dr dv plus the radial part. Okay? And there is another coordinate system which is u is t minus r star, which is very similar to it, but it is describing not the infalling but the outgoing observer. This is du square. Okay? So you can see actually from this, for example, that if you draw R versus V, okay, and here we have constant V, okay, and this is our value of horizon, okay, at R equals 2 mg. You'll find actually that the light cones are going like this. Okay? And here, as it crosses the horizon, it will be like this. And it is tilted more here. Okay? So in other words, as it crosses the horizon, it's not going to do like the Schwarzschild coordinate. Okay? It's not going to behave like the Schwarzschild coordinate. It's not going to be completely squeezed. Okay? So it will keep an angle, which is a sign that the physics is not, or the metric is actually good description. Okay? Now let's go to another coordinate system, which I'm using u and v together. All this journey is to actually end up with what we call theoretical description of a black hole, which is important to understand the physics of the black hole and drawing the whole space-time in just a finite region on the board. So using u and v together, I can write down the ds as minus the factor 1 minus 2 mg for r dv du, again plus the radial coordinate. Okay? And in fact, in this description, we have pushed away the horizon to an infinite value. So we'll find that the horizon is at u plus infinity, and the horizon also at v equals minus infinity. Okay? So we were able to push the horizon infinitely far away. Okay? But of course, it's important to have the horizon at a finite distance. So we are going to a new coordinate system, we call it u prime and v prime. And in this new coordinate system, we have v prime, for example, is e to the v over 4 gm, and u prime is minus e to the minus u over 4 gm. And in this case, it is very clear that you have a description which is not problematic at all at r equals to mg. Okay, you can see that at r equals to mg, there is no problem with the picture. Okay, but since we are dealing with still null coordinates like coordinates which is preferred by null rays, okay, so it's better to actually deal with non-null coordinates, or like usual coordinates, okay, coordinates like time and radial distance. So we are going to do that here. We define a time-like coordinate t, which is half v prime plus u prime, which is going to be r over 2mg minus 1 to the half e to the r over 2gm sinh of t over 4mg. This is t, and another coordinate r, which is very similar, but with minus sign, half v prime minus u prime, and exactly the same form here, having okay. So this is r over 2gm minus 1 to the half e r over 2gm. Okay, this is cosh of t over 4mg. Okay, I'm going to use these two coordinates, and this is it. This is the end of our coordinate transformations. Okay, so let's now use this t and r capital to understand what's going on with these black holes. Okay, a very important relation that we are going to need is the following. From these definitions, t squared minus r squared is going to be 1 minus r over 2mg e to the r over 2mg. Okay? This is relation 1. Another relation is t over r is tanh t over 4g. Okay? So these two relations are very important to draw for us. What are the curves of constant r? For a constant r small curve, we will have a hyperbola, right? Because this is going to be constant. And t squared minus r squared equal constant, this is a hyperbola. Okay? Also because r is larger than 2mg. Okay? And now, for constant t curves, we are going to have straight lines, because I can write this, of course, as r. So this is the slope of the line for constant t. Okay? And what else? When I write down the metric of this thing here, I still have an angle plus or minus 1 as a slope between t and r. So I have t2, g3, m3 over r e to the minus r over 2 gm, and here I have minus dt. This is important to know the light cone. So you can see that the light cone actually is just the usual light cone, as in Minkowski space. Okay? So let's draw this. So we have t, and r, okay, and you can see that the light cone is going to be just t equals plus or minus r plus some constant here. But also for the horizon, okay, the horizon is at r equals to mg, and this is going to be 0. So you have also r is related to t, okay, in the same way, okay. So t is plus or minus r is going to be also the horizon. So let's draw the horizon here. So this is our horizon. Okay, and this is r equals to mg. Okay, and you can see that this region here is describing any r larger than 2mg, and here is describing r less than 2mg. So this is inside the horizon. This part here is inside the horizon. This part here is outside the horizon. So this is kind of Minkowski space as we go far. I'm going to call this part, this whole part, okay, part 1. And this part here, part 2, and this part here, part 3, and this one here is 4. Okay? Now let's see, for constant r curves, I get the hyperbola here for r larger than 2mg. And this is going to behave like this. This is going to be like that. Hopefully you can see the red color. Okay? And here is going to be like that. This is constant r surfaces. Okay? And of course, r here is larger than 2mg. r here is less than 2mg. So we have to end up a singularity here at r equals 0. Okay? Okay, this is the constant r curves. What about constant t curves? Constant t curves, let me draw them with a different color, which is green. And we will see that the constant t curves, okay, are straight lines. Okay? So they are going to be like that. Okay? So if a particle coming from late time, so this is early times, okay? Early times, late times, later, okay? So this point describing an object, okay, at earlier time with some large radial coordinate, okay? And now it's getting closer to the horizon here, and then it's getting closer again here if we have another curve like this one, okay? So you can see that every body here is infalling into the horizon, okay? Everything here is kind of infalling into the horizon, okay? And what about inside the horizon? Inside the horizon, if you also draw the time, you will see that the time is going like that. Okay? So this is an earlier time, and this is a later time. And you can see that the particle was here and then start to be here. So you can see that any future time-like curve, okay, in this picture, in this region, region 2, is going to end up with the singularity, okay? Because time curves are straight line and getting actually up, okay? And the curve here we have is getting closer and closer to r equals 0 because these are constant r curves. So you can see whatever object that we have is going to fall into the black hole singularity at the end of its journey. Okay? So everything here is going to fall into the black hole singularity at the end of its journey. This is not necessarily here. Here you still have a chance to escape. But for an object which is not doing anything, of course it will be attracted to the black hole gravitation, and it's going to fall into, okay, the horizon. Okay? These four regions, we can think of them as follows. Of course, region 1 is the Minkowski space and its asymptotic region. Okay? 2 is the inside of the black hole, as we said. What about 3 and 4? Okay? In fact, 3 and 4 are a kind of mysterious because 3 has to be a copy of 2. Okay? So we need to have here again r equals 0. Okay? And almost like a mirror image of 2. But the only difference is that trajectories are actually going outside this region, okay, not inside. So this is why many relativists think of it as a white hole, okay. This is the main reason that they think of it as a white hole. But is it something physical? Is it something realistic, really? Nobody knows, okay. So this is region 3. What about region 4? Region 4 is very strange because it's not accessible at all from the point of view of any observer here, any physical observer in region 1, okay, or region 2. It's inaccessible, okay. The only way to access 4 from our region is through space-like trajectories, of course, which is not physical. Okay? So in a way, region 4 is completely detached from our world. But what is the interpretation of region 4? It is, some people think of it as the other region in Einstein-Rosen bridge. So if we think of Einstein-Rosen bridge as So this is our region 1, and this is region 4. Okay? And here lies inside the black hole, this is our black hole, this is the white hole. Okay? And here is region 2, and here is region 3. Okay? And region 4 is the asymptotic region of the white hole. Okay? So this is the full description of Schwarzschild black hole, which is called Kruskal diagram. Okay? Which is very important to understand all the possible regions, all the possible mathematical regions in this black hole description. And I think I'll end up here and I'll take questions if anybody has any question. Okay. No question? Too much information? Too little?
Where is the region where there is normal orbital motion?
Normal what?
Orbital motion.
Everything physical is here.
Minkowski very far away, but there is in the middle area which is not Minkowski and not black hole and not white hole.
Right. It's here. It's in one.
It's in region 4. In one?
Yeah. So everything is physical outside of the black hole is in one.
Okay, so where is the Minkowski? I can't see.
Minkowski is the far region here.
Ah, okay, so I missed what you're talking about.
Yeah. Because
Minkowski
as R goes to larger and larger than 2mg is here.
Yeah. One is in between, right?
What?
One is in between 4 and the other region, right?
One is here. This is 1. This is 2. This is 3, and this is 4. Okay? All right. So, since no questions, stop here.